Welcome to our math video. Today we're going to speak about optimization. In the simplest case, an optimization problem consists of maximizing or minimizing a real function by systematically choosing input values within an allowed set and computing the value of the function. Take for example y equals f of x. First, we have to define the independent variable, which would be y, an object of maximization or minimization, and then we have to define the dependent variable, which are variables chosen to achieve a desired objective. Now, what do you collectively call the maximum and the minimum? That will be extrema, which we can divide into the local and global extrema. The local extrema would be the maximum or the minimum of a function in the neighborhood of the point, while the global extrema would be the maximum or minimum value of a function in the range of the function.
Talk about the branch of optimization that is the first order condition. Given our previous definitions, we can clearly explain how we can find possibly the maximum and the minimum. But first, when we look at the original equation, we first have to derive y and then set the whole equation equal to 0. That equation, however, is the derived equation, not the original equation. So here's an example. The example is y equals 2x squared minus 5x. And when deriving such equation, it turns into, through a process, 2 times 2x to the 2 minus 1 as it's the normal deriving rule, minus 5 times 1, removing the x. So it concludes as being y prime is equal to 4x minus 5. So that is the derived equation. And now we have to make this equal to 0. So to find the maximum and the minimum. So 0 is equal to 4x minus 5. So we put 5 on the other side, change signs obviously, as 5 equals 4x, and then we divide 4 on both sides, and x will end up equaling 5/4. However, that does not suffice. You might ask why. Well, this is why it's not enough. It gives the tangent to the curve, which is indubitably 0. However, it doesn't distinguish between maximum and minimum. We know that this is an extreme point, but we do not know if it's on the lower side or the upper side. So when the f prime of x is equal to 0, in some occasions, these are the inflection points. Alright, now moving on to the second order condition after trying to verify if it's a local maximum or a local minimum. As in the first order condition, we found if it was a critical point. Now we are moving to the specifics into being either a local maximum or a local minimum. So when looking at the function f of x of 0, it would be a local maximum if and only if the second derivative is less than 0. This is in terms of the function f double prime of x 0. Now, on the other hand, when looking at the local minimum, f of x of 0 would be a local minimum if the second derivative is above 0. So to find that, we go into the specifics, and when looking at the maximum, it has to be, when looking at the curve, when the curve moves up from the left side, the line goes flatter. In that occasion, that means that it would be a local maximum. When looking at the minimum, the line has to move down, and from the left side, and slowly getting flatter. And that would therefore be a local minimum. So when looking at these critical points, we have to find, for example, in the minimum, that the slope will be negative, so we'll be going down here. So therefore, the double prime of f has to be above 0.
Hello, now I'm going to walk you through a full example in order to find the local maximum or local minimum of a given function. Suppose that we have this function, which is f of x equals to x squared minus 5x plus 8. First, we will have to do the first order condition in order to find the critical value of x. So we will have to derive this function, which would be 2x minus 5, and then equal it to 0. If we equal it to 0, it would be 0 equal 2x minus 5. The next step would be to solve for x. If we solve for x, we would get the following. Five equal 2x, and then x equals 5 over 2. Okay, this is the first step in order to find the local minimum or local maximum. So once we have the critical value, now we have to see whether if it's a local minimum or local maximum. In order to do this, we would use the second order condition. The second order condition is really simple. We will have to do the second derivative. So the second derivative would be it would be 2. If the second derivative is bigger than 0, then it means that we get a local minimum. So since we got the number 2, it means that it's bigger than 0, and we have got a local minimum for the function.
Another one of the applications of the derivative is to prove that a given function with a given point has a local maximum or local minimum. In this case, we have been given this function at the point hk, which is 0.8 and 1. So the first step that we would have to do is to replace h as the x-coordinate, 0.8, and k as a y-coordinate, 1. Now that we have the completed function, the next step would be to derive it. In order to derive this, we would apply the chain rule, which would mean that this is multiplied by 1, and then the 2 goes down, leaving with negative 6 times x minus 0.8. Now, in order to prove that this is a maximum point, we would need to find the slope when x is smaller than 0.8 and the slope when x is bigger than 0.8. And we can make a prediction already, thinking that when x is smaller than 0.8, we would get a positive value for the derivative, whereas when x is bigger than 0.8, we would get a negative value for the derivative. Let us try with a value that is bigger than 0.8. For example, 1. When we plug it into the function, we would then do 1 minus 0.8 times 6, which would leave us with a value of negative 1.2. Now this value is smaller than 0, which means that it is sloping down, just as our theory confirmed. We can apply the same concept with a value of x that is smaller than the point, and therefore we can predict that we would get a positive slope for the derivative. Now, plugging it into the function, we would have 0.2 minus 0.8 times negative 6 would give us a derivative of 3.6, which is bigger than 0. As we can see, the slope being bigger than 0 implies that it is sloping up. And since we plugged 2 points, one which is smaller, one which is bigger, and we got the corresponding slopes, one which is sloping up and one which is sloping down, we can conclude that the point 0.8 and 1 is a local maximum.